We're into chapter 11 last time. Really in this chapter, we're talking about electrons. And the idea mostly of what we'll be discussing is electrons as they sort of travel from one energy level to the next. They will give off a certain amount of energy in the form of a wavelength, a length, I'm going to spit that out, I think. A photon with a specific wavelength that corresponds to the energy that allows them to transition from one energy level to the next. As electrons go from a lower energy level to a higher energy level, that's a sort of endothermic process for the atom. It needs to absorb a certain amount of energy to allow those electrons to transition. And as they drop down from higher energy levels to lower energy levels, they need to release the same amount of energy to allow them to do that. We talked about sort of the idea of quantized energy as well. The idea of electrons, for example, will gain and lose energy in enough amounts to make them able to fully do the transitions from one energy level to the next. Again, they'll never sort of find themselves in between energy levels. So they sort of gain and lose energy to get themselves either one energy level, 2 energy levels, 3 energy levels, going up or down. We saw some equations that are important in terms of waves, and that was C is equal to the wavelength times the frequency. Remember, typically the wavelength is in meters. The frequency is 1/seconds or reciprocal seconds, which is also a hertz. It's also what 1/seconds is, hertz. And the C is the speed of light, which is 3 × 10⁸ meters per second. And that's a constant that you should always have available to you. So if you know the wavelength, you can figure out the frequency pretty easily. If you know the frequency, you can figure out the wavelength as well by just basically the same calculation as the wavelength. For example, is C over the frequency, or the frequency is C over the wavelength. There is a relationship between energy and the actual wavelength and the frequency. We have sort of a longer wavelength. That usually results in a sort of lower frequency and lower energy, as opposed to a much shorter wavelength. Shorter wavelength usually has a much higher frequency and also a higher energy associated with it as well. So we did sort of an example there at the end. So we're going to just try another one here. Let's see, we had, what is the frequency of a wave with a wavelength of, let's do 540 nanometers. A reminder that nano is 10⁻⁹. All right, so take a second there, see what you come up with. I'll do it as well. Hope we'll end up at the same spot. Okay, so take a look here. So in this case, we have the wavelength, which is 540 nanometers. We are looking for the frequency. So once again, we can use our formula that we had before. Remember, you do really want to make sure that the wavelength is in meters, and that is because C, again, is also in meters. Otherwise, unit-wise, it will not cancel out correctly. So you got to make sure everybody's in the right units. So nano here is 10⁻⁹. A reminder that when you see something like that, what that means is in 1 nanometer, there would be 10⁻⁹ meters, or 1 × 10⁻⁹ meters. So not the other way around, which again is a very common mistake that people make. So that's what I'm going to do. I'm going to convert my wavelength there into meters. So I'm going to take 540 nanometers, do a little dimensional analysis here. 1 nanometer on the bottom, 10⁻⁹ meters on top. Nanometers here will cancel. That'll get me 5.4 × 10⁻⁷ meters in this case, I believe. At this point, we have our arrange our equation. solve for frequency, which would be the speed of light divided by the wavelength, putting in our numbers here, and again, making sure that we do use our exponent button here. 5.4 times 10 to the minus 7 meters gets us divide the first number correctly there. That would help. Divided by 5.4 to the minus 7. Looks like maybe 5.6 times 10 to the 14. I can only be 1/2 seconds as your units, which again, you can leave like that. You could also write like this, and it is also a hertz. So, you know, any of those 3 units are the same deal. You can leave them in as well. Any questions on that calculation there? Okay. So when energy comes off, when come here, there you go. When energy comes off in the form of the wavelength, a photon of light with a specific wavelength, it could fall in different parts of the electromagnetic spectrum, and this is electromagnetic spectrum. And we see a couple of things here when we look at sort of our settings. We got on this side a longer wavelength. On this side, a smaller wavelength. So that means left-hand side where we have a smaller wavelength is going to be much higher in energy, lower in energy on this side. So if we look at things sort of on the right-hand side there, we have radio waves, which you know, is why we could listen to the radio in the car. Not too bad for us. If we continue to the left there, we get to microwaves, so a little bit more energy. Could cook our food a lot faster, right? Just 3 minutes, you get like a pizza, it's all good. The infrared, as we come to a little bit more energy, a little shorter wavelength, it's usually where we feel heat and stuff like that. Then we come to the visible part of the spectrum right here. So that's the visible part of the spectrum where we see colors, or Roy G. Biv, right? And even with our sort of colors, there is a distinction in terms of energy associated with them. So you can see red over here has a longer wavelength than, say, the violet or purple region, and thus it would be lower in energy, the red, than, say, a violet color. So we do see sort of increasing energy as we go that way across sort of our colors there. Then we come to the ultraviolet section. Why we put sunblock on when we go outside, right? So we don't get too burnt from the rays. Then obviously a little shorter of a wavelength, we get into X-rays. Also why they put a lead vest on you, right? And leave the room when they shoot the X-rays, because a lot of energy associated with that. And then we get the gamma rays, which we talked a little bit about, I think, when we were talking about some radioactive stuff, particles, when we talk about the atom. But gamma rays, again, is really just sort of pure energy. Radioactive particles have, or rays really, has no charge associated with them. So as we go from sort of right to left on this picture, we're increasing energy, decreasing wavelength. You do need to know these, not necessarily the actual numbers where everybody breaks off, I think, but you do need to be able to put them in order from things like lowest energy to highest energy, longest wavelengths to shortest wavelength, highest frequency, lower frequency. So that type of order is what you need to know, not exactly numbers or anything like that. That also includes the visible part of the spectrum and the colors. So you do need to know the colors also sort of in that same order, higher energy, lower energy, longer, shorter wavelength, and those type of things. Any questions on that? Obviously, when we did the flame test the other day, we got guys coming off in the visible part of the spectrum, where we see color. The color that we see, for example, is complementary to, say, a solution. It looks red to us. It's actually complementary color to the wavelength of light that's actually being absorbed. So later on in chemistry, you'll do some experiments where you'll use something that was just like a spec 20, a spectrophotometer, and you'll set the wavelength to the complementary color to the color of the solution that you see. Some people think like, wait, hey, my solution is red, so I should set my wavelength to red. But when you use something like a spectrophotometer, it's basically the complementary color that's being absorbed. So you actually set it to the opposite color. So as atoms and molecules emit or absorb these discrete quantities of energy, as we talked about, kind of like the staircase approach, allowing them to get from one energy level to the next. The energy associated with that can be found by this equation here, equals h times the frequency. So that's an important little equation there. H is Planck's constant, which is this one right here, 6.63 times 10 to the minus 34 joules times seconds. Those are the units. So joules is a unit of energy, and obviously seconds is a unit of time. And that works good if we just think about the units associated here. H is joules times seconds. And obviously frequency is 1/second. So the seconds cancel. And we end up with joules when it's all said and done. And we use this particular equation. So if you know the frequency of light that's coming off, you can figure out the energy associated with that. And if you take this equation here and you tie it in with the equation we were just talking about, and you solve for frequency, which is c over the wavelength, and you take that and basically put that into there, it gives you another very common version of this equation, which is hc divided by the wavelength. What that means is, frankly, if you know the wavelength of light coming off, you can figure out the energy associated with it, because h is a constant, so that's a number you always have, and c is a constant, which is the speed of light. So these two equations here allow you, if you know either the frequency or the wavelength, you can figure out the energy associated with that energy that's coming off. So in our sort of conversation, as the electron transitions, giving off that light in the form of a wave, at a specific wavelength, you can figure out how much energy was needed to make that transition of an electron from one energy level to the next. Any questions on that there? So why don't we try one here just to put it together? Why don't we do the one we just did? So what is the energy associated with a wave with a frequency of, what did we just calculate there? 5.6 times 10 to the 14 reciprocal seconds. All right, take a second there to come up with. Okay, so let's take a look. So in this case, we do have the frequency given us. So remember, that is basically our frequency. So in this case, we can actually just plug right into our h times the frequency. H, once again, is a constant, so you always have that number. You should know that number. It pops up a lot, joules times seconds. We're going to times it by our frequency here, which was 5.6 times 10 to the 14 reciprocal seconds. Again, the seconds here will cancel each other out. And if we do that there, we get a number probably, I'm assuming. Maybe if I hit equals. We end up with 3.7 times 10 to the minus 19 joules. First off, any question on that calculation? A reminder that if you find yourself sort of off by a little bit, probably the way you're punching in, not using your exponent properly on your calculator. Now, just to show you again that although in this case we started with the frequency, if we backed it up to the original problem where we calculated that the wavelength was actually 5.4 times 10 to the minus 7 meters, and that was from 540 nanometers. With this guy here, we can also figure out the energy by using the other form of the equation here, by just putting in our guys, which is our constants up on top. Divided by, once again here, the wavelength should be in meters for everything to properly cancel out. And that's because now meters will cancel. Once again, seconds will cancel. And if you do it with the other version of the equation, you should get the exact same number, basically. And again, it just allows you, as you can see, regardless of which one you have, you will end up with basically the same number. So again, it allows you, either you have wavelength or you have the frequency, you could use these versions here to figure out the energy associated with it. That would be the energy associated with that wavelength of light coming off. If it was the atom absorbing the energy, it would be this positive number. If the electron was actually transitioning from a higher energy level to a lower, it would be given off. It would be the same number, except that it would be negative in terms of that, as the atom would be giving off the energy and be exothermic. Any questions on those calculations there? All right. As we've been talking about, excited atoms will eventually relax down, giving off that photon of light as the energy is being really emitted from the atom. Now, when this happens, especially with elements, sometimes spectrums can be found. And there's really kind of two types of spectrums that we come off, RC, and they're emission spectrums, which means there basically happens when the electrons are transitioning down from a higher energy level to a lower energy level, and they're emitting it off. You could do this just like we did with the flame test the other week, just stick it in a flame. Obviously, it gains a lot of energy, excites all the electrons. Also, an electrical discharge tube, you know, if you've ever seen that, you'll also can do that and excite the electrons that happen. Now, when we see things that happen, like it's red hot when you put an iron bar and it starts to glow, that's this visible glow is the portion of the emission spectrum that we can see by the eye. The heat coming off is kind of from the infrared part of the spectrum. But a common feature of emission spectrum from heated solids and things like the sun, it's a continuous sort of spectrum. So there's sort of a continuous spectrum, and there's also sort of what is referred to as a line spectrum that we'll talk about. In a line spectrum, we get distinct lines of color, for example, that come off when you look at it through a prism. In a continuous spectrum, you know, you kind of see everything sort of coming off all at the same time. So the emission spectrum of atoms in the gas phase give more of a line spectrum, and these are distinct colors that we see. And each color is really a result of electrons transitioning from different energy levels. And as they do so, it's that energy that's being given off that corresponds to somewhere in the visible part of the spectrum. So somewhere in that visible part of the spectrum where we see our colors, we will see specific lines coming off at specific wavelengths with specific colors. It is so specific for every element that you could actually identify what element you're dealing with based on the number of lines you sort of see, the colors that you see, and the wavelengths at which they come off. So every element will give sort of a different line spectrum. Sometimes they do experiments where you take like a little spectroscope, kind of look through it, has a prism, and it kind of separates everybody into those lines when you look at a emission lamp. And when you do, you see something like this. So these are the four sort of excited lines that we see from a hydrogen atom. And each of these correspond from electrons going from different energy levels. So for example, if we think about energy levels, n equals 1, n equals 2, n equals 3, n equals 4, and so forth. These are what are referred to as the principal quantum number. It is a fancy word for basically the energy levels. And basically n equals 1 is the ground state, and everything above it sort of excited states. So, you know, as an electron goes from, say, this to the fourth energy level, and it decides it wants to drop back down to the second energy level, and maybe we have an electron on the second energy level that decides it wants to drop down to, say, the first energy level. Again, as they do this, they have to release the energy to allow them to drop down to a lower state of energy. The result of that is we see a line of color at a specific wavelength. We could also make a fairly good prediction, perhaps. So, for example, if my electron went from the fourth energy level to the second energy level, versus my electron that went from the second energy level to the first energy level, which one would require more energy? Yeah, the 4 to 2 would require more energy, right? Because it's now gone through a couple of different energy levels. The result of that is, because it's going to be higher in energy to do so, we would expect the wavelength of light coming off to be a longer or shorter wavelength. wavelength, right? So shorter wavelength, longer in energy. So we would expect that probably the color that we would see here would be more of a shorter wavelength, more towards maybe the violet or blue side, versus the transition here, where it's transitioning only one energy level, which is a lot less energy. We would expect a longer wavelength, and maybe that's more towards the orange or red side spectrum. We would see sort of that color. So like this guy over here on the right would be probably a result of a transition that occurred from a sort of lower energy level to another, not as big of a jump as opposed to these guys over here, where it probably resulted from an electron transition, maybe 2 or 3 sort of energy levels. And that's why we see the different colors basically come off. Any questions on that there? So Bohr had an idea of an atom, and Bohr's model of sort of the atom, or explanation of what we see in the hydrogen spectrum, which we just looked at, is one that's sometimes referred to as the planetary model. Basically, the idea was, you know, we have our nucleus and we have these sort of orbits, if you will. And so these orbits here would be our different energy levels. So this would be like our n equals 1, our n equals 2, our n equals 3 sort of level. And what he thought was these electrons are, you know, kind of circling around like sort of planetary model and moving around in nice, pretty circles. And what we're seeing in terms of those lines, there's these electrons transitioning, you know, from one energy level to the next. So maybe you got an electron out here, he decides to come back down to a lower energy. Again, the atom is going to give off that energy in the form of a wave, and it will result in a specific color that we see. So Bohr's model is sort of not so correct, and everybody past hydrogen. So once you sort of get more electrons involved, it doesn't really work so well, but it works really nice to explain sort of what we're seeing in the hydrogen atom. So the idea is we have these electrons in these circular orbits. They have to stay in those orbits. If they decide to transition, they will gain enough energy to make that transition. So once again, as they would want to maybe move from, say, this energy level down to here, they would give it off in the form of a wave that has energy equal to h times our frequency, basically, that we just talked about. And once again, it's sort of this quantized energy idea where electrons will be able to go from one energy level to the next. They won't find themselves sort of trapped in between energy levels. They will fully transition from one to the next. It's a prettier picture, I think. So the emission of radiation by these hydrogen atoms could be explained in terms of electrons dropping from that higher energy level to the lower energy level, giving off that wavelength and a particular color sort of emitted. So let's talk a little bit about the idea of quantum numbers. We're just going to talk about really the first one, which is n is equal to 1. There are 4 quantum numbers, which explain why electrons and where they are at and how many electrons there are in there. But the principal quantum number, again, is referred to as n, and it is the energy level. So that n equals 1 is the ground state. Anything considered above it, n equals 1, like n equals 2 through 7, are excited states. So n typically has values of 1 through 7, where n equals 1 is the ground state. And basically 2 through 7 are excited states. The idea here is as we go up in terms of n value, we're getting further away from the nucleus. So the electrons are further away from that positively charged nucleus, not held as tightly as obviously ones that are in lower energy levels. So as we talked about a second ago, here's some prettier picture what we were talking about, but we have this electron that basically has now transitioned 1, 2, 3 energy levels. That's going to be, again, a lot more energy than our electron that just transitioned the 1 energy level. So again, our kind of red color that we saw probably from that transition here, again, more of that violet purple sort of color, going to probably come from that longer sort of transition in terms of energy. Now, the idea of quantized energy versus a continuous spectrum. So like the sun and stuff will give a spectrum that's sort of continuous. We pretty much get everything coming out. So again, it's sort of analogous to, I think we'll see a picture here, but in a continuous spectrum, if you walked up a ramp, you pretty much could walk and stop anywhere along the way if it's just a ramp. The more quantized energy, which is sort of what we see happening over here with our atoms, again, is more like the staircase approach that we might have talked about last time. You'll either find yourself on this step, this step, this step, or that step. Again, you won't find yourself sort of in between steps. And again, that's sort of how electrons transition. They do transition by gaining and losing energy to completely do that transition, as we can see here, as opposed to something like the sun, where we just got everybody coming off at once. So let's talk a little bit about the wave mechanical nature of electrons. Why is the electron in the Bohr atom restricted to orbiting the nucleus at certain fixed distances? De Broglie sort of came up with this idea, and he didn't really do much of experiments. He just sort of theoretically thought about it, and he had really the idea of sort of what is referred to sometimes as the standing wave. So like on a guitar string, if you pluck the string right, you can see the wave. But that obviously wave cannot go anywhere because the string is attached to the guitar, right? So it's sort of the same idea here. In an atom, we have that positive charge in the nucleus. We have the electron, which, you know, can sort of behave like a wave, but it is sort of attached to the atom, if you will, by the attractive force to the nucleus. So although it can have sort of wave-like function, it is attached there by its attractive force to the nucleus. And that's sort of the idea of like a standing wave. And basically at certain points, there will be no amplitude, right? Which are sometimes referred to as a node, where you have no amplitude on a wave. And the same thing will happen with electrons. And really what this is sort of, again, leading us into is the idea of the dual nature of light. Again, a particle like an electron can also function very much like waves, and waves could have particle-like functions. So they can basically work both ways. And that was sort of the idea here behind de Broglie. Now, the other important thing that sort of moved us away from sort of Bohr's idea of this planetary model, where we're kind of moving away from the idea of I have an electron, it's in an orbit, and it's traveling in pretty circles and stuff like that, is the idea of Heisenberg's uncertainty principle. And basically what Heisenberg's uncertainty principle is, it basically says that it's impossible to know simultaneously both the momentum and the velocity of a particle like an electron. So the more you know sort of about its location, the less you know about how it's traveling. And that really does go against the idea of Bohr and his orbit model, because obviously if an electron was in a circular orbit, a bad example would be you could put your finger right there and eventually the electron should come back around, right, and hit it as it's traveling in a nice pretty circle. And again, electrons and particles like this do not really travel that way, and they do travel pretty randomly. So what all this helps us sort of move away from is the idea of electrons in orbits traveling these pretty little circles, away from the Bohr model to a more sort of model where we say, I'm not really sure how the electron is moving, not really sure exactly where the electron is, but I could have a pretty good guess as to where there's a high probability of finding an electron. And Schrodinger had a bunch of equations. If you ever take physical chemistry, you'll do all those equations. But basically the idea here is we move away from the idea of electrons in orbits to this idea of electrons in what are referred to as atomic orbitals. And really what atomic orbitals are really probability maps. So they're probability maps within an atom as to where there's a high probability, I guess even a low probability, of finding electrons. And we would expect, obviously, that there's a high probability of finding electrons near the nucleus because the nucleus is positively charged. Electrons are negatively charged, so we would expect a pretty good high probability of finding it near the nucleus. So if this was our nucleus, and this was sort of the electron density, we would find a pretty high probability here. But as we would sort of fan out from the nucleus at some distance, the probability would start to decrease. Not to say there couldn't be an electron there, but the probability of finding an electron will start to decrease, obviously, as you move away from that positive charge. Now, just because there's a high probability of finding an electron in a particular location within the atom doesn't mean we know how it's moving, how it got there, when it's there. It just knows that, there's a very good chance that somewhere in that probability area, we would find an electron. So when we talk about atomic orbitals, and we'll talk about it here, there are a few different types. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And these are all the different types of atomic orbitals where electrons are thought to be housed within an atom. And here's sort of a probability map, and maybe you can see it better on the screen here what I was drawing, but obviously towards the center there where we would assume the nucleus would be, there's a much higher probability of finding an electron there. It's much darker, and as you can see, as you sort of fan out from the nucleus, it gets lighter and lighter, which means there's a less of a probability of finding an electron in that particular area. So let's talk about these different atomic orbitals, which is basically where we house electrons in an atom. And once again, they are really, for the most part, probability maps, so sort of theoretical, mathematical distribution of where we would find electrons. One really important thing as we talk about these orbitals is any individual orbital, be it an S, a P, a D, or an F, could only hold a maximum of 2 electrons. So any individual orbital, no matter which one it may be, an s orbital, an individual s, a p, a d, or an f, could only hold a maximum of basically 2 electrons. The first type of orbitals is actually the orbitals that start on the very first energy level. So on the n equals 1 energy level, there is only what is referred to as a 1s orbital. A 1s orbital means the one, it's on the first energy level, and it's an s orbital. An s orbital basically is a sphere, and they are found on every single energy level, except they just kind of get larger as they go up from one energy level to the next to accommodate the extra electrons. So if you went to the n equals 2, you would find a 2s orbital. If you went to the n equals 3 level, you would find a 3s orbital, and so forth, continuing up. Now, the 1s orbital, again, could only hold 2 electrons. So, you could only pop 2 electrons into each of those orbitals if those arrows are representative of an electron each. Again, it just gets larger as you continue upwards. And again, this is sort of the theoretical shape of it, with the highest density of electrons being found towards the center, where we assume the nucleus is sort of located. And here's the shape of them. Again, you can see it's the same shape, just gets larger to accommodate the extra electrons as it goes from one energy level to the next. The next type of orbitals are p orbitals. And there's actually 3 different types of p orbitals. There's a px orbital, a py orbital, and a pz orbital. And that's sort of their orientation in 3-dimensional space, if you will, like in math, x, y, and z. There's one on the x, y, and z. There's sort of like a figure 8, they're sometimes referred to, or a teardrop sort of shape, where the node here is sort of where we would expect the nucleus to sort of be, and probably high electron probability happening near that sort of nucleus. Now, they do not start until the second energy level. So once again, on the first energy level, there's just the 1s orbital. When we get to the second energy level, we have our 2s orbital. Then we have our 2p orbital start to appear. So it's not until we get to that second energy level that we actually do start to see p orbitals. And there are 3 different p orbitals, which means if we take all 3 of these p orbitals together, that is what is sometimes referred to as a subshell or sublevel, depending on their book and who wrote it. So that is sometimes referred to as a 2p subshell or a 2p sublevel. That encompasses all 3 of the p orbitals on that particular energy level, which means if I filled up the entire 2p subshell, how many electrons could I put in there? 6, right? 2 into each. We would put 2 electrons into each. They actually go in one at a time, we'll talk about, and then come back. If I want to know how many electrons in a 2p orbital, how many could I put in there? It is actually just 2. So an individual orbital can hold 2, but if you filled up the entire subshell of 2p, you could put all 6, 2 in each. Any questions on that? Starting at the second energy level and continuing on through 7, you have p orbitals that occur. 3p, 4p, 5p orbitals. Again, they're all pretty much this shape here, as you can see, kind of that teardrop shape. And once again, you kind of envision the nucleus being there. And as you can see, the highest probability kind of happening near where that nucleus would be thought of as happening. The next type of orbitals are d orbitals, and there's actually 5 different d orbitals. And d orbitals actually don't appear until you get to the 3rd energy level. So once again, on the 1st energy level, we have our 1s orbital. On the 2nd energy level, we have our 2s, a very badly drawn 2p subshell. Put it a little bit closer, maybe. And then when we get to our n equals 3, once again, we have a 3s. We got our 3p, and that is 1, 2, 3, 4, 5. I'll squeeze them in. That is where we start to see our 3D subshell occur. Once again, the 3D subshell would be all 5 of those guys together would be our 3D subshell, which once again means if we maxed out our 3D subshell, each one could hold 2, and there's 5 different ones. We can max out with a maximum of 10 electrons if we filled in all of those. So we could do 10 electrons max here. Not that you necessarily have to fill them all, but you could, and you would get 10. Basically, d orbitals kind of look like 2p orbitals stuck together, which is why they got 2 different axes sort of happening there as you go through here. Except for the last one, looks like a p orbital with a donut going through the middle, but most of them look like 2 p orbitals together. There's also f orbitals. I'm not sure where that slide went, but there's also f orbitals. And f orbitals actually begin on the 4th energy level. So when you get to the 4th energy level, that is where we first start to see our f orbitals. So once again, n equals 1, we have our 1s. N equals 2, we got our 2s, our 2p, or n equals 3, got our 3s, 3p, and our 3d. And finally, we get to our n equals 4, 4s, 4p, 4d, and our 4f, which should have 7 of them. Ran out of space, but there should be 7 of them there. So understanding where these guys start is really important for electron configuration. So 1st energy level, just S's. 2nd energy level, P's start. 3rd energy level, D's start. And 4th energy level is where our F's start. So what happens with these orbitals is electrons essentially will go into the orbital's lowest energy first and continue on that path. So They will continue putting electrons into the atom, lowest energy, until they put them all in. So they would go obviously here, then here, then here, and continue that sort of path. Now, when we have hydrogen alone here, which has just one electron, the energy of all the orbitals here are the same. So for example, if I took this entire place here, which is the n equals 3, which by the way is sometimes referred to as a shell, our level, all the orbitals there are basically exactly the same in energy. And by the way, if I wanted to max out the n equals 3 shell or level, how many electrons could I put in there? It would be 18. We could go 2 there, right? 4, 6, 8, 10, 12, 14, 16, and 18 electrons. Yeah. There's 7. I just ran out of room there. So that's why I wrote the 7 on top. So there should be 7 little dashes, and there'll be 7 of them. Yeah. Now, you could draw it out like this, but nobody wants to draw it out like this. So a quick way to answer that question is you basically take 2 times n squared, and that will tell you basically how many max electrons on a shell are level. So the one we just did was 3. 3 squared is 9. 9 times 2 is 18. This is the n equals 2 level here. 2 squared is 4. 4 times 2 is 8, and you can put 8 electrons if you filled up everybody there. So you can quickly calculate it by taking n squared, which is the energy level, times it by 2. You want to make sure you square it first and then times it by 2 when you do that math. By the way, we never get there, but there are different orbitals, and they just go alphabetical after F, just go G and so forth, but we never get into any of those in terms of electron configuration and stuff like that. Now back to energy here, what we see with hydrogen, since there's just one electron involved, all the energy of the orbitals are all exactly the same. But when we start getting multiple electrons involved, electrons, right, are negatively charged, which by default means they really don't want to be near each other. So it does affect sort of the energy of the orbitals, and this is what happens. So as you can see, everybody's even, and then there's a lot of change that occurs in the different energy of these orbitals or subshells, and it does affect the order at which electrons go into the atom. So once again, they would start here at the 1s, go to the 2s, then to the 2p, then to the 3s, then to the 3p, and this is where people get confused. Actually, the 4s orbitals are lower in energy, so they actually will go into the 4s first and then back to the 3d, and that pattern happens all the way through 5s back to the 4d. So because of this difference in the way the electrons go in, you do have to make sure that you kind of know the order correctly. And this is a really easy way to sort of know it. This is the order at which electrons go into the atom. We always start up here. And basically, if you know that S could hold 2 electrons, P could hold 6 in the subshell, D could hold 10, and F could hold 14 max electrons. You pretty much could write any electron configuration that you need. And what we do is we basically just go to the end of the arrow and then come back this way and come to the end, come back, and just keep zigzagging back and forth. The nice thing about this, and what I was talking about earlier, was if you remember that on the first energy level, that is where S's begin. If you remember on the second energy level, that is where P's begin. If you remember on the third energy level, that is where D's begin. And if you remember on the fourth energy level, that is where F's begin. You basically could recreate this really quickly for yourself. You just put the numbers underneath. So this would be like 2s, 3s, 4s, 5s, 6s, and 7s. Remember, energy levels go to 7. And then you can fill in this guy, 3p, 4p, 5p, 6p, 7p, and then 3d, 4d, 5d, 6d, and 5f. So just like that, you can really recreate this for yourself by just remembering 1, 2, 3, 4, and just put the numbers underneath. Truth be told, even if you screw up and go too many numbers here, you'll probably be okay in most cases. Even if you didn't stop at the right number, you probably won't get down there anyway. So this is a really good way to sort of remember it and make it. And like I said, if you kind of know how many electrons you can put in there and that sort of chart, you should be able to write any electron configuration you need. Yes. In terms of the electrons, any further than that. So 60 questions. And that is the order there. So let's talk about writing electron configuration. When we write electron configuration, it tells us basically how the electrons are distributed within the atomic orbitals. The number of electrons in a neutral atom should equal the number of electrons in the atomic number. I'm going to spit that out right again and try that again. So the atomic number, which is the number of protons, obviously is the positive charges in an atom. So the number of electrons, if it's neutral, should be the same. I think that's what I was trying to spit out there. So let's take a look at hydrogen here. Hydrogen has 1 electron. So we would start at the very top of our chart and we would do 1s1. And that is the way you should write it, 1s1. We'll talk about what each of these things mean. The first one is the principal quantum number, so that's the n number. The s tells us that the electron's hanging out in the s orbital, and the 1 on top, which is a superscript right here, tells us basically how many electrons there are in the orbital or subshell. And that is the way you should write it, like this, 1s1. There's no dashes, no commas, no weird things that people like to write. Another way that we could represent electron configuration is by drawing what is referred to as an orbital diagram. And when we draw an orbital diagram, you can either use boxes or lines to represent each of the orbitals. And we use arrows to represent each of the electrons. So in this case, we would have 1 box or 1 line for the 1s orbital. And our first electron into the orbital always goes in the upward direction. That is what is sometimes referred to as having positive spin, plus 1/2. That's a quantum number as well. That's what's referred to as the spin quantum number. And an arrow sort of pointing in the upwards direction is considered having plus 1/2 in terms of a spin. And it's always the way the arrow goes into the box, the first one in any orbital pointing in the upwards direction. Any questions on that there? Continuing on, let's take a look at the next one, which is helium. And there's a really important sort of reason how we put our next electron in. And with helium, we have 2 electrons, which means we could put both electrons into the s orbital. And there's an important rule, which is known as the Pauli exclusion rule. And it says that no 2 electrons that are basically in the same orbital can have the same 4 quantum numbers. So we don't go too deep into quantum numbers here regularly, but n is a quantum number, L is a quantum number, m sub L and m sub S. These are the 4 quantum numbers. They basically represent the energy levels, the orbitals, and the orientation and the spin of the electron. So basically n is the energy level. L is basically the type of orbital. M sub L is basically how many orbitals, really their orientation in 3-dimensional space. And m sub S is the spin quantum number for the electrons in an orbital. So that's basically what those guys are. So Pauli's exclusion rule says that if you put 2 electrons in the same orbital, they should never end up with the same 4 of those numbers. And what allows us to sort of change it is actually the spin. So when we look at something like helium, which is 2, we would do electron configuration of 1s2. Now, in terms of our box here, our orbital diagram, I'll give a couple of options here, a few options. Only one is right. We could put the electron up and up. The other option would be down and down, perhaps, and maybe up and down. So the correct option is this. This gives our electrons different quantum numbers. So if I did the quantum number for this particular electron, not that you need to know how to do this, but this would be n is equal to 1, L is equal to 0, m sub L would be 0, and m sub S here would be plus 1/2, which would be the identical numbers for this guy, which means that cannot occur. This guy here, if I did the electron for this guy, n would equal 1, L would equal 0, m sub L would equal 0, and m sub S would equal minus 1/2, which would be the same for both of those electrons, so they cannot be. If I did this electron, it would end up with these 4 quantum numbers. If I did this electron, it would end up with these 4 quantum numbers. And really the only difference between those 4 quantum numbers is the spin. This guy is minus 1/2. This guy is plus 1/2. And that allows it not to violate Pauli's exclusion rule. So since we don't really go deep into that, you will in 1A. But basically the rule is arrow goes up first, second arrow goes down, and that's basically will not violate Pauli's exclusion rule in this particular case. So when we do get to helium, that's where we come into this situation. And again, the correct orbital diagram would be first guy up, second guy down. So within each individual orbital, that is basically how electrons go in. First one up, second one down. And again, that allows them not to have the same 4 quantum numbers. Just the spin of the electron is basically what's different between those two. And that's enough not to violate Pauli's exclusion rule. Any questions on that there? All right. When we do have electrons like this, one going up, one going down, this is what is sometimes referred to as paired spin. They essentially cancel each other out, plus 1/2, minus 1/2. They sort of cancel each other out in terms of their spin. So paired spins when we got 2 electrons in the same orbital heading in opposite directions in terms of their spin. Continuing on to lithium, which is 3. We would now have to go to 1s2, which would fill it. We would come back and zigzag back to our next spot, which would be 2s. And in this case, we just need 1. This means on this lithium here, there are how many electrons in the first energy level? There are 2 electrons in the first energy level. And the second energy level, there is 1 electron. Yeah, so we have 2 electrons on the lower energy level, 1 electron on the higher energy level, which in this case would be 2. To do our orbital diagram, we would need 2 boxes. And I'll tell you, it's not energy correct. I just don't have room to go up, but typically you would go up in terms of energy. So I'm just going to go sideways, not correct in terms of energy, but we'll save room that way. We'll go up, down, and now when we get to our next orbital, the first one will once again go in the upwards direction, and it should look something like that there. Any questions on that there? Continuing on here to our next element, which would be beryllium. We have 1s2. Again, we're going to zigzag back to 2s2. Can I put any more electrons into 2s2 at this point? I cannot. It is filled because it has 2 electrons, and that's as max you can put in the s, which means if I have more electrons, I then need to zigzag back and come to my 2p orbitals, which would be next. Doing our orbital diagram here, again, 1 up, 1 down. They're paired, 1 up, and now our 4th one comes down. And as you can see, there's no more room in that box. So our next electrons would have to go to the next lowest in energy. And that occurs at boron, which is number 5 there, I believe. So let's take a look at boron, which is 5. This would be 1s2, 2s2. Again, continuing down the arrow path and zigzagging back will get us to 2p here, 1. How many electrons are on the second energy level? There are all of those, and that's a grand total of 3 if we count the numbers on top, right? And on this first energy level, there are 2 electrons that are basically happening there. On the second energy level, we got 2 electrons hanging out in the s orbital, and we got 1 electron hanging out in the p orbital, basically. So if we drew our boxes here for boron, we need a few extra boxes here for our 2p. Again, they could have 3 different orbitals. So 1 up, 1 down, 1 up, 1 down. Now the first electron, just like before, goes up and actually goes to the orbital on the left there. And when we put that, that is actually the px orbital. That's the py orbital, and that would be the pz orbital. Basically, that's happening here. Now, how many more electrons can we put in that p subshell before we're filled? P subshell could hold more electrons, right, before it's completely filled at this point. We do have options of where we could put the next electrons. We could put it in the same box. We could put it in the box next to it. And there actually is a rule that we follow to tell us where we should put the next electron. And that is what is referred to as Hund's rule. Hund's rule states that the most stable arrangement for electrons is the one that gives the greatest parallel spin. So if you remember, we just saw that up and down is paired spin. So parallel spin would be everybody heading in the same direction. So parallel spin would be going in the same direction. And that tells us basically when we put our next electron in, we're actually not going to pair it up. We're going to actually go to the next orbital next to it. And if we do that for carbon, we would have 1s2, 2s2, 2p2. And how the electrons go in: up, down, up, down, up. And now the next electron will actually go into the py orbital next to it, heading in the same direction to maximize the parallel spin. If we put it in the first orbital, we would have paired off the spin and not maximize the parallel spin. So this is a much stable sort of arrangement. So when you have multiple orbitals in a subshell, this is how they always go in. They go in basically one at a time, and then you pair up. So that's basically how they go in. They fill one at a time, then go back and basically pair everybody up with their P subshell, D subshell, and F subshell, where there's multiple orbitals. That's exactly how each one goes into those subshells, one at a time upwards. They come back and then pair off. Any questions on that there? All right, we'll lay it up there for today, I think.